Greetings. Welcome to our sixth lecture. Is it the fifth lecture? But today we'll be talking about, we'll be discussing linear algebra, introductory to linear algebra. I know that in the previous lessons, we discussed limits and intro and continuity. We spoke about epsilon delta definition. But that is the basis of calculus. So basically calculus, it's what most universities do in first year. Then there's some universities that also do linear algebra. Other universities, they reserve linear algebra for second year. But otherwise, so today that's what we're going to be discussing. And again, obviously the topic is very big. So we're just giving the preliminaries, or the introduction to this linear algebra. Okay, I think you already know what algebra is. Algebra is just those solve for x, when you play around manipulating the equations, making some of the formula, that is doing the algebra part. But otherwise, the linear algebra is a branch in mathematics. Remember that mathematics is very huge. First of all, this idea that maths is numbers, please remove that from your head. That is not true. Yes, application of mathematics is in numbers, but mathematics is not numbers. You can do mathematics actually with no number whatsoever. Okay, talking about this linear algebra is a branch in mathematics, and this branch actually gets to focus only on linear equations. Yeah, that linear equation, the straight line, yes. So basically, we get to only focus on that. This topic of linear algebra. I know that actually it seemed like, but what can you do with linear equations? All you can do is just to move them y-intercept or play around with the slope or find them intercept in some way, solving simultaneously. But actually, application of these linear equations is very huge. Very, 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 very huge. It gets to be used in banks. It gets to be used even coding your phone. Just for you to lock your phone and lock it and all those things. There's a whole lot of linear algebra applications happening there. And for the people that are going to do computer science, I'm not talking about IT, I'm talking about computer science. They're going to, as they study further, they're going to see a lot of application of this linear algebra. And that's why they need to do maths, so that when they get to that stage, they can be able to understand what is happening. Like I said, linear algebra is just a branch in mathematics. Remember that when you guys are still in high school, you are taught things as one. You're given a bit of calculus. Calculus, I'm not talking about calculus, I'm talking about that part where you have to find the maximum area or the maximum profit of whatever that you'll be dealing with, or finding that first principle, having to find the gradient of the function using first principle. So there's just a bit of that, because even though we see that part of actually finding the derivative, you'll be surprised, but it's a very huge branch in mathematics. There's a whole lot of application, because you maximize everything. You maximize your profit, you maximize your area, you maximize your cost, you minimize your cost and all those. So it's a very big topic in mathematics. So there's some mathematicians that actually some companies can come to them and say that, this situation, I want to minimize the cost. Then they can play around and try to see, actually do the calculus there, minimize the cost, maximize the profit, and tell them how many people you should hire, how many machines you should buy, how many cars do you need, which routes to you. Actually, that is a whole lot of mathematics happening there, even for buses. Just for buses, to know actually what bus should leave at what time, what route to take, how many buses do we need. That is linear algebra, by the way. Okay, before I get to talk a lot, I think maybe we should just get into the topic and get to discuss actually what we want to talk about today. Like I said, linear algebra is a very huge topic. So there's no way we can finish the entire topic in just one lecture or in just one lesson. So today I'm just giving the elementary, just to give you a feel of actually what is this linear algebra, what really happens in this linear algebra. I think, like as usual, I'm going to switch off my camera so that we can focus on the on the lesson. Yeah, there it is. Okay, let's start first. So normally on your Cartesian plane, right? I believe you know that in one dimension, that's when you have a number line. So in two dimensions, that's when you have a Cartesian plane, the XY, the X-axis and the Y-axis. So that Cartesian plane normally is called, when you have coordinates that are two-dimensional, meaning the coordinate XY, we call those, we say that they are rectangular coordinates. There's a huge types or different types of coordinates. So those ones are called rectangular coordinates. And for a straight line in a rectangular coordinates or in a Cartesian plane, this is a general form. I know that we are used to the y is equals to mx plus c, but that's when you want to make y to be independent. I mean, y to be dependent on x and x to be the independent variable. But generally speaking, this is the form of a linear equation, meaning you have a coefficient of x, you have a coefficient of y, and you have some constant. So basically, this is a general form of a linear equation. And like I said, we also have 3 dimensions plane. And those also are called rectangular XY coordinate system. If you want to imagine it, and remember that the XY plane, if you want to visualize it, it's just saying that you can either go forward, backwards, or you can go sideways, left or right. So basically, that's why the Cartesian plane, it looks like this. It means actually you can move either going back, forward, or going backwards, or you can go left or go right. So that's what the Cartesian plane is, right? Obviously, you can go diagonal, meaning you're mixing both going forward and going sideways. But otherwise, you cannot jump. It means actually you are rooted on the floor. You can either move left, right, and all these things, even if you turn around, but otherwise you do not jump. So, but otherwise, when you start jumping, that's when we move to the, it's called the XY plane. I mean, XYZ. So basically the Z coordinate, it means actually now you're allowed to go up, and on the XY, this is the normal Cartesian plane that we know, the one on the floor. So remember, actually, this can go on that other side, and even the X can go on that other negative side. So it means on the floor, that's when you have the XY plane, the one that we're used to. The XY plane that we're used to is the one that on the floor. But once you start jumping, it means actually either jumping or going underground. So initially, even for the z-axis, it also goes down. So basically, if maybe, so this point, it gets to be called 0, 0, 0. So basically, there's the origin. You can see that we have 3 dimensions here, meaning x, y, and z. So this is x, y, and z. Yeah. So if you want to think about it, think about the corner in your house, at the corner. So remember, you have a wall going up, you have the other one going on the left, and you have the one going the other direction. So basically, it means if maybe you're focusing at one wall, you can either go backwards or forward. There's the XY plane on the floor, but once you start jumping around, that is the Z axis. So if we're using such coordinate system, our linear equation in that sense, it becomes of this form, this AX, meaning A needs its coefficient, B needs its coefficient, C's coefficient, and a constant. And please note that actually these coefficients, maybe 1 or 2 of them can be 0, but not both of them, not all of them. So for in the Cartesian plane, A and B cannot both be 0. It does not make sense. And in Cartesian plane, A, B, C, not all of them can be 0, because otherwise you'll just have some constant is equals to 0, which is just 0. So that is not a straight line anymore. Generally, we can have, so basically these linear equations, we did explain what is a linear equation in 2 dimensions, a linear equation in 3 dimensions. So sometimes, so these are the examples of linear equations, but otherwise, sometimes we can generalize and work on more dimension. So basically, as you can see from here, we have 2 dimensions, which is x, y. Here, for the XYZ plane coordinate system, we have the XYZ. So basically, these are the ones that are called unknown. So the X and your Y, those are they are called the variables are the ones that are called, they get to be called unknowns. So same thing for here. So the XYZ are the unknowns, then the ABC, and those are the coefficient. Then D is just some constant. So to generalize things, we define a linear equation in the n variables. So remember, it means n unknowns, and in that case, it can be represented in this form, whereby we can, I hope you can see that from here. Remember that we said we're talking about n variables. So that's why you see that we end up having xn. It is possible that actually your unknowns are infinite. So in that case, you just have a lot of infinite. So that there is a particular situation which is like that. But otherwise, each and every x, it has its coefficient. So remember that all these AIs, or the A1, A2 until AN and B, all those are constants. And we say that AIs, they cannot, all of them cannot be zero. Maybe 1 or 2 or 3 and all that, but not all n of them can be, all of them cannot be zero. Otherwise, you will not be having a linear equation. So now, so basically, as I said, this equation 1 is the general form. So basically means actually looking at this equation here, this one of ax plus by is equals to c is a special case when n is equals to 2, and here it means n is equals to 3. So normally, when your n is finite, remember we're talking about the variables. So normally when the variables, we don't use the subscripts. Subscripts, I'm talking about this one at the bottom. So we don't use, so like here we have finite, we only have 2. That's why we have ax plus by, and here we have x, y, z. So even if maybe there's 4, we can have x, y, z, and k, something of that sort. But so that's when we use, when we have many of them, that's when we get to use these subscripts. But otherwise, if it's finite, then we just give them, we just label them. For example, here, if our n is 2, then we can just have xy. We can just call them xy. And remember, the a1 and a2, those are just coefficients. Both of them cannot be 0. Then from 3 dimension, instead of having x1, x2, x3, you can still do that. It is allowed, but normally just to avoid the confusion, we just call them x, y, z. And again, remember that think about the Cartesian coordinate, the Cartesian plane, the one that you guys know. You can have equation, a straight line going through the equation, and normally we can have this is equals to, let me generalize it and just say ax, whereby a is some constant. So basically it means actually our y-intercept is 0. So for such equations whereby the y-intercept is 0, meaning here when b is 0, then means you're talking about straight lines that passes through the origin. That's what it means to a special case when b is 0. So even for n variable system or a equation with n variables, if our b is equals to 0, it means actually we call such a linear equation, we say that it's homogeneous. And in graphical terms, it means it's a linear equation that passes through the origin. That's what it means. And in that case, x1, x2 until xn, those are our variables. Please note that actually, let's get to define what makes linear equations linear. Because sometimes we need to be clear, but sometimes people confuse that. But I guess in this case, we want to be clear actually what is a linear equation and which one does not qualify to be linear equation. So far, I believe you have seen that actually it does our variables, we don't have any product or root of variables or a squared or our variables all just have a constant, and the power of or the exponent of our variables, all of them are 1, and we do not have any x, y, or multiple of a product of variables. So for that, for linear equations, we do not have trig equations, we cannot have log functions, we cannot have exponents, and also not. So basically all of them needs to be linear, meaning the exponent needs to be 1, and we cannot have a product of variables. So all this means this one is in 2 dimensions, and you can see that this one is in 4 dimensions. And here you can see that our B is 0. So this is a homogeneous linear equation with 4 variables. Yeah, this is 3 variables, n variables. So basically all these are linear equation. But once you start including square, then it's not a linear equation again. And look at here, for this example, we have x, y. So this is a product of variables. So in that case, it is not a linear equation. Here with trigonometric, we have sine. It is not a linear variable. We have roots here, or x to the power 1/2. It is not a linear equation anymore. So now, when you have, because sometimes, if you remember from your simultaneous equation, sometimes you can have more than one equation. So suppose you have a set, a finite, meaning limited number of this linear equation. So you have a number of linear equations that you want to solve simultaneously, like for simultaneous equations that you know in Cartesian plane, where the graphs intercept, right? That you end up having a solution of a coordinate, your x and y, and for, I believe you remember with quadratic sequence in your grade 11, when that one of Tn is equals to an squared plus cube, sorry, an cube plus bn squared plus cn plus d. So basically, if you substitute your T1, T2, T3, you end up having this A, B, C, D to be unknowns, and you want to solve. So basically you have 3 unknowns, and you end up having 3 equations, and you want to solve 3 equations all at the same time. So such cases, we call such cases, we say that you have a system of linear equation. Or sometimes, because we know that we're dealing with linear system, we just sort of with linear equations, so we just say that it's a linear system. So like I said, a linear system or a system of linear equations is when you have a finite number of linear equations with finite number of unknowns. And actually sometimes even these unknowns can be infinite, but the functions need to be finite for you to say that it's a system of linear equation. Basically, if you look at this equation here, so you have this one is when it's one equation of 2 unknowns. We can still call it a system. Here we have one equation with 3 unknowns, is still an equation. Otherwise, if you look at this, you can say that if you want to solve for x and y from this, you can say this is a system of linear equations with 2 equations and 2 unknowns. And here, this is also a system of linear equations, except that you have 2 equations, but you have 3 unknowns. And basically, actually, for the fact that you have number of equations and the number of unknowns, it tells you the kind of solutions for you to expect. So, so general linear system. So generally, a linear system of m equations. Remember, m equations, the number of equations that you have. The n unknowns is the number of variables that we have. So in this case, if we have n variables, and we have, so it means now that we have more than one equation, that's why this B, it has a subscript. So basically, if we have m equations, you can see that you have first equation, second equation, third equation. If you have m equations and the unknowns is x1, x2 until xn, so it means that the number of unknowns is n. So you have n unknowns and m for mother. M number of equations. So basically, that is how we define system of linear equations with m equations and n unknowns. So in this case, you have system of linear equations with 2 equations and 2 unknowns, because the x and y are the ones that you were trying to figure out. Let's give an example. So we have system of linear equations here. We have 3 equations. Equation 1 with B1 being 9, equation 2 with B2 being 1, equation 3 with B3 being 0. So basically, this is a system of linear equations with 3 unknowns and 3 equations. So basically, when you have this, just like in quadratic linear equations, you'll be trying to solve for A, B, and C. And for you to do that, you need to substitute to find T1, to find T2, to find T3, and try to find all, try to solve all those equations using a simultaneous equation. But actually, that method of solving the linear equations, the way we did with the quadratic linear sequence, it can be very long, especially when you have number of unknowns being too much, being many, or the number of equations being many. So to solve that using your hand, it can take you forever, because sometimes you solve and you have many variables. And in that case, you need a computer to solve that. So basically, it means we need to teach a computer how to calculate that a bit faster so that we can get the results quicker and make the decisions based on those calculations. Okay, coming back to this example. So, and this discussion is actually get to talk about all those methods, or to talk about that method that gets to help us solve them and these system of linear equations a bit quickly. So now we come into a definition of what's called a matrix. So basically a matrix, you can go look at the definition of a matrix here. So basically a matrix is an array of numbers. So basically some numbers that you put in sort of not really a box, but it's just some array. So we could just call it array, so we can have 1, 2, 0, 1. So these array of numbers, they have dimensions as well. So basically, as you can see, matrices or matrix, if it's one, if it's more than one, then we call them matrices. So these matrices, they have the dimensions. Remember, the matrices, they come from system of linear equations. So the system of linear equations, you have the number of unknowns, you have the number of equations. So for that gives, it means actually each matrix, it has a dimension. So the dimension is the one that tells us actually the size of the matrix that you're dealing with. Dimension. So the dimension is the one that tells us actually how many equations do we have and how many unknowns do we have. So in this case, we have 1, 2, 3 equations. So that is 3, the number of unknowns. Remember that the number of unknowns is 1, 2, 3. So we have 3 unknowns as well. So you call this the dimension of this metric. We say that it's 3 by 3 metric. I'll come back to explain actually this line. So basically we have 3 equations and we have 3 unknowns. So for that we say that it's a 3 by 3 metric. Right, so meaning in this case, this metric we say that is we're going to say that it's a 2 by 2. You can have, for example, let's say you have 1 minus 4 and say 3. So this is also a metric, except that you have 3 equations. You have equation 1, the equation with 1, second equation minus 4, third equation is just 3. So in this case, it means that, and you see that we have 1 row, one column of these numbers. So this we say that is a 3 by 1 metric. So remember we said, so the dimension basically is just the number of rows. Number of rows times the number of columns. The number of columns. So the rows, basically we said we're talking about the number of equations, and the column we said those are the unknowns, our variables. I hope that part is clear. So this metric, remember that this the metric that we've been dealing with so far. This one, it is an equals to, because sometimes you can just have a part whereby you just have these equations. You just have these. I can't call them equations because equation means actually equals to something. Right? So if they are not equations, then we just call them expressions. So So we just have these three expressions. So in that case, it means that you are going to have a 3 by 3. But otherwise, if we develop a metric coming from, let me see if I can erase so that it looks a bit neater when we, no, wait. Let me just see if I can remove this from your eyes. Sorry for the delay. I just want us to all be in the same page so that you guys are not confused. So we spoke about the dimension of a metric, and we said the dimension of a metric talks about the number of rows a metric has, or the number of columns a metric has. Yeah, so we want to continue here and actually get to know actually what do we do with these matrices? How do we get to solve this system without actually trying to solve them using the normal way that we know of. I remember when you solve these linear equations, so far in high school, we've learned that either you can use the graphical method. So the graphical method is when you draw the equations and wherever they intercept, that's a solution. That's the first method of solving a system of linear equations. The second one is when you use substitution method. Substitution method, it means actually you take one variable, make it you make it subject to the formula, or you make it, you make it the subject to the formula, then you substitute it into another equation. And then the third method was the one of elimination. You try to make sure that the coefficients of these linear equations are the same. And when the equation, when these coefficients are the same, then in that case, you can eliminate by adding or subtracting equations and all that. So that's what you've learned so far. So right now, we want to learn another method called playing around using matrices. So basically, this one is called augmented metric, meaning comes from the column of B's and the column of all these variables. So as you can see, this 1, 2, 3 are all the coefficients of X. This coefficient here is 1. So 1, 4, 6, which is the second column, and the third column also. So basically we develop these matrices from the coefficients of the unknowns and all the column of the constants. So basically what we do, so basically we can call this one, we call this row 1, we can call this one row 2, and lastly we can call the third one, we can call it row 3. So basically right now we already have an augmented metric that came from the so we just took the variables from the metric and the constant to make one metric. So such is called an augmented matrix. So the process that we are about to get into is called the raw operations. So basically the raw operations is the same thing as what you would normally do with simultaneous equation by multiplying some constant on some equation throughout, and when you get to do the eliminations, when you get to add equation 1 and equation 2 to substitute, to eliminate and all that. So basically that's what we're going to do, but except that here we call them raw operations. So if you look at, the plan of these raw operations is to come to a point or be left with a metric whereby we have diagonally. So here we can left, I'm just going to write them A, B, and C. So basically to end up having this metric that has zeros elsewhere and end up having 1 in a diagonal line. So this is the plan, or this is where we want to go. So basically we can see that here we already have 1. So the plan is to make this 1 to be 0, to make this guy to be 0, 0, 0, 0, 0. So basically, so that, and this 4 we want to make it 1, and this -5 we want to make it 1. So these numbers we do not matter, we don't care. Remember that this is the column that comes from the Z, from the coefficient of Z. So if this part is 1, it means that Z is equal to this number. And if everything else is 0, it means the y is equal be equals to that number. If everything else is 0, it means that 1 will be equals to that number. So basically the operations that we're going to do right now are the ones that are going to make sure that we can be able to find our solution. So like I said, the first step is to turn these guys, these 1, 2, 2, 3, 6, and minus 3 to make them to be 0. It's up to you, the process or how you get rid of them. So the first thing that we're going to do, if we take the first equation, right? 1, 1, this one of 1, 1, 2. Let me just erase again so that we can see what we're talking about. Ambuya tshela logama lakubiza dalisizeni nakumahlalela. Okay, I'm almost done. All right. So basically, if you look at what we have so far, right? Remember we said this one is row 1, row 2, and row 3. So like I said, we want to make this guy to be 0, right? So maybe to make this guy to be 0, take row 1, multiply with -2. We can keep row 1 as it is, right? So we can see that here 1, 1, 2, 9, it did not change. But row 2, remember we can be able to play around with the equations, add equation 1 and equation 2, just like that. So basically we take equation 1, right? And we get to multiply it with -2, right? So it means that here we're going to have -2, it means we're going to have -2, here we're going to have -4, and here we're going to have -18. I hope that part is clear. So after multiplying this first row or first equation with -2, then add it to the second one. Because you can see here, our new term now is -2. Remember, we're keeping that in mind. Row 1, we said we're going to keep it as it is. So we want to make this guy here to be 0. So we take the first equation, multiply with -2, then add. Or we can multiply it with 2, then subtract. Right? So if even now we add, we have -2 plus 2, it gets to be 0. -2 plus 4, it gets just get to be 2. -4 plus -3, it gives us -7. I hope that part is clear. So basically what we did here, we said minus 2 times row 1 plus row 2. So in other words, to develop, let me just make an arrow to make row 2. So basically means to make a new row 2, you're going to take row 1, multiply with -2, add it with the old row 2 to make the new row 2. So that's what happened. Then row 1 and row 2, we just took them to be like that. So I'm just going to write dash just to show that actually we did not touch row 1 and row 3. Row 2 is the one that actually we got to play around with. So now, remember, like I said, we want to make this 2 and this 3 to be 0. So we want this guy to be gone as well. So we want this guy to be 0, and we get to do the same thing. Multiply row 1, because remember we already have a 0 here. So the part 1 is done. So now we want to make this 3 to be 0. And for us to be able to make this 3 to be 0, we multiply row 1 with 3, then subtract. Or multiply row 1 with -3, then subtract. So that's what we get to do. So if we multiply row 1 with -3, then add, it means actually this term was going to be 0. That's what happened here. Remember we said we took -3 in the first equation and we added it to the third equation, right? So we got 0 here. If we come to the here, so remember that this is going to be 3. So I'm sorry, we said we multiply by -3. So -3 plus 6 becomes +3. The remove multiply by -3. -3 times 2 is -6. So -6 plus -5, it gives us our -11. And so basically row 1, we took it as it is. Row 2, we took it as it is. Then we started with row 3, trying to make sure that, so we started with row 2 and row 1, making sure that actually we get these guys to be 0. Because when that is done, then we are on the right path. So like I said, the goal is to have the ones in the diagonals, right? So the plan is to have all these ones in the diagonal. So we already have these two guys, which is good. So what we can rather do is try to make sure that this guy, sorry. So basically we can try to do is to take, because we already have zeros here. So we can take these 3 to be 0. And for 3 to be 0, we can multiply row 2 by 3 so that this part is 6. Then take row 3 multiplied by 2. It also becomes 6. So we can make this guy to be 0. So as you can see from now, like I said, we want the diagonals. So when we have the diagonals, it means actually we want all the ones. So here, because we already have a 0, we can make this guy divide by 2 so that we can make him 1. So if we divide by 2 through aloud, so it means actually this part here is going to be 1, and this part here is going to be -7/2. The third part, we end up having -17 all over 2. And yeah, so that's what we have so far, because we wanted this guy to make sure that he's 1. So now the plan is to make sure that actually this guy gets to disappear. And by the way, we have not lost our equations. Remember, we're solving a system of linear equations. We have not lost our equation, because actually this is what we have so far. Equation 1 has not changed. Our new equation 2 is y minus 7/2z is equals to -17/2. And equation 3 is also as the same. Yeah, so our idea now is to make this guy 3 to be 0. So for us to be able to make this 3 to be 0, remember we want to take this 3 to be 0. So we multiply row 2 by 3 and row 2 by -3, then gets to end. So we take -3 times the second equation, then we added 8, right, to the third equation. Yeah. So after adding it to the -3 times the first row, adding it, we end up now having this part to be 0. Remember that this part is already 0. So it does not going to change. So to get this guy, we said we multiply this one by -3. After that, we add him to u. So -3 plus 3 will give us to be 0. And here we're going to have minus times -7/2, that is just 21 over 2, because 7 times 3 it's 21. So after doing all those, even the last column, the one of the constant, as you play around with this, what we have here, make sure that actually even those columns of B, they also change. Sorry. Yeah, so this is what we have so far. So we left equation 1 as it is. Equation 2, after dividing by 2, we left it as it is. So right now we have from this equation, you can see that we have -2 here and -3. So basically the interpretation algebraically, it means actually the first row we still have xy plus 2z is equals to 9. Second equation, we do not have, it means the variable of x is 0. So you have 0 times x. And the third equation, it assumes that actually both x and y, the coefficients are 0. So, but now, if you get to look at this equation, remember, this was the case. Remember these were all the x, column of x, and this is a column of z, column of y and the column of z. So basically, if you look at this, it means actually, if we equate this equation here, it means actually we have minus z, we have -1/2z is equals to -3. And so it means actually we already have the value of z. We can take this z, substitute into equation 2, because equation 2 does not have x. We only have yz, then substitute here and get y. And after now you have your Z and your Y, you can come and substitute into the first equation. So basically that is the plan, and that's what we mean when we talk about raw operations. And this raw operation, there's different types of raw operations, by the way. This one is called the Gaussian elimination. Gaussian meaning this is G. Okay, bad handwriting. Gaussian is in Gau. Then Gaussian is double S. Gaussian elimination. So basically, Gauss is a very old mathematician who came up with this theory of this is what you can do. I hope that part is clear. So like I said, now from here we can read our solution for Z, then work our way up. But again, after some time, there's another mathematician that came called Jordan. Jordan is in G-O-R-D-A-N. So Jordan actually was studying the method of this guy Gaussian, and actually he got to improve it. And after doing that, then we started having a method called the Gaussian elimination. I'm sorry, Gauss-Jordan. Sorry for that. So we have this method called the Gauss-Jordan. So basically what this method of Gauss-Jordan does is to remember that Gauss said, no, now you can read your solution. Then Jordan said, but no, you don't have to wait there. Why just not continue with these raw operations until actually you get to the part whereby you have these matrices of the leading ones. Yeah, so Gauss-Jordan is the method that makes sure that actually we get this kind of metric. Because when this is the case, you can just say that if this is x, y, this is x, y, and z, it means actually y is equals to c, and b is equals, y, x is equals to b, and remember we said this is going to be x, y, and z. So it means x is a, y is b, and z is equals to c. So in that case, you can just read your solution without any trouble. So basically, if you look at this metric now, we have these leading ones. We call them leading ones because before that it's 0. So we have these leading ones. So it means actually we need now to turn these guys, these 3 items, these 3 babies, we need to turn them to be 0 as well, which we can think of it as very easy, because if you get equation 1 and equation 2 and equation 3, if you multiply equation 3 by positive 7/2, then if you just add the equation, then you are able to eliminate some other variable. So that's what you do. And so we took -1, we multiply the second equation to the first equation. So basically it means from here, because we want to get rid of this guy, we multiplied this by -1 and we added to the second equation. So that's what we did. And after doing that, this is what we get. So you can see that we already have our zeros, and we also have these bottom zeros as well, which is good. So it means the next bottom to get rid of this one here. So you continue with the raw operations, and after you're done with the raw operations, there you are with your metric. You can see now we have all these leading ones, and when that is the case, you can just read and say that it means that z is 3. It means y it's 2. All right, and again x, which is the first entry, so it means actually this x it gets to be our guy here. So such metric we so from here, as I said, you can see that the solution is going to say x is equals to 1, y is equals to 2, and x is equals to 3. And in this case, you say that our solution is unique. Because at times when you don't get a unique solution, or sometimes you get infinitely many solutions. So be on the lookout for that. But otherwise, I think I've already thrown some sentences that I think that maybe you might not be familiar, or some keywords that you guys are not familiar with. And I'm hoping that since I spoke about the raw equivalent form, the leading zeros, augmented metric, what did I also, did we get to talk about? Gaussian elimination, Gauss-Jordan elimination. So those are some of things that you can actually, those are the some of things you can go back to go and read on them and actually get to try to see if you can understand what is happening. But otherwise, I think what we did today here is just introduction to this linear algebra. So give yourself time to go through these slides. Remember, we're sharing the slides in the video. So after that, you can just go through the slides at your own pace and get to understand what exactly is expected of you. Otherwise, see you next time, and sanitize, keep safe, and enjoy the semester. I think we are 2 weeks away from the result, getting our results. So all the best with that. I think that should be all from me for today.